Hey APCalc class, we're going to take a look at the notes for section 6.1, which is finding the area between two curves. And the idea here, we've been working with finding area under a curve by using an integral, and that would take us to the area, from the curve down to the x-axis. Well, sometimes it's necessary to find a different area that would be just the area between two given functions. So in the pictures we have here, we have two parabolas that intersect, and one of them's opening upward, one's opening downward. And if we were interested in finding that area, the pink area that's between those two parabolas, we can kind of look at what we've been working on. So the parabola, the blue one that opens downward, the area under that curve is in green. And if we were looking at the interval between 1 and 3, that would be what we'd have here, would be those green shaded blocks. And if we're looking at the area under the other parabola that opens upward, the red one, then we have this area that's in blue. Now thinking about, if you subtracted out this blue area from what we have here, in the green that's under the red one, if we subtract those two, it's going to yield, just the area between the curves. And so that's kind of the setup for how do we find the area between two curves. So what we need to do is take the bigger function values, which is, I say, the top, the function that's on top, minus the function on the bottom, and then that's going to leave us with what's between the two. And so that's basically the setup. So if f of x is the blue parabola here, and that's the one that's bigger, the one that's on top, minus g of x, the red one, that should give us our area that's between that pink area, the area that's between the two curves. Okay, so that's kind of what this statement reads right here. If f and g are continuous functions where g is less than f, okay, then we'd subtract it in this order, f of x minus g of x, the area of the region bounded by the graphs of f and g, and the vertical lines x equals a and x equals b, meaning the bounds of your integral right here. Okay, and we saw a lot of times those are determined by where the functions intersect, and they intersect at the x coordinates of x equals 1 and x equals 3, but that's typically how you find your bounds, is where the functions would intersect, unless you're told some other information. Okay, so first example, it's stating that we're supposed to find the area between the region that's between the curves y equals x squared plus 2 and y equals negative x. And they do want us to sketch this out and shade the region in question. Now we're also bounded by the y-axis, which is x equals 0, and then x equals 1. So that actually kind of tells us what our bounds of our integral are going to be, 0 and 1. But when we shade this out, when we sketch it out and shade, it kind of gives us a good idea of what it is that we're looking at and what our bounds should be. So this first function is just a parabola that's shifted up 2. So I start with my vertex 0, 2, and I'm only really going to 1. So when I put in 1, I get 1, 1. I know it's a parabola, it's concave up, and so it's kind of curving up like this. All right, and then the other part of this is just a line with a slope of -1 and a y-intercept of 0. So I can start at 0. Slope is -1, and again, since I'm only going to an x value of 1, I just get this little line segment right here. Now these lines, x equals 0, x equals 1, those are going to give me my other bounds for kind of enclosing this region that I have here. Almost looks like a trapezoid, except we got this little curve here. Okay, so this green shaded region is what I'm going to determine the area of. All right, so when I set up this integral, again, I want to take the top function minus the bottom function. Now the top function is the parabola in this case, so I underline that in blue. The bottom function is the line. And really what I'm doing is I'm finding the distance really between, sometimes we call them representative rectangles that we draw in here, and we're basically summing up all of these little rectangles that would be in here. But to get the heights of those, we got to take top function minus bottom function. Okay, so there's top minus bottom. We'll simplify that. We can combine any like terms. That's going to end up being a plus x, so it looks like this. All right, so now I'm going to integrate this, and so that's going to give me x cubed over 3 plus x squared over 2 plus 2x, and I'm going to evaluate that from 0 to 1, right? So we take f of 1 minus f of 0, and I plug a 1 in there. That'd be 1/3 plus 1/2 plus 2, and then minus f of 0, which is just going to be 0. Okay, so I've got 1/3 plus 1/2 plus 2. That'd be 2/6 plus 3/6 plus 2. I get 2 and 5/6 for that one. Okay. Now you can easily check this with a graphing calculator too. And I typed this in. So we do our integral from 0 to 1 and it was x squared plus x plus 2 dx. And it verifies 2.83 repeating would be the same as 2 and 5/6. Okay, so many of these would be non-calculator questions, but as we're practicing, I'd encourage you to just go ahead and check your answer with your calculator on some of these. Okay, next ones, I have sketched these out just to save a little bit of time. But we've got a parabola that's shifted up too, but it opens downward. So that's what I'm going to have right here. Parabola with a vertex of 0, 2, opening downward. And that's our top function, because the other function is just the line y equals x, which is this red line right here. So the area that's bounded between them, I've got shaded in green again. And we're going to take the parabola function minus the line, 2 minus x squared minus x. Okay, and we're going to, find the intersection points. So that's what the other part you're going to have to do. Determine where they intersect. That the line intersects the parabola at -2, x equals -2, and x equals 1. So those are my bounds here. Okay. Now I'm going to integrate this. 2x minus x cubed over 3 minus, this would be x squared over 2, and we evaluate from -2 to +1. So I first plug in the 1, and I'm going to get 2 minus 1/3 minus 1/2, and then minus. Be careful with your minus. Make sure that when you're subtracting, use parentheses, because you're going to total up all these parts here that are in parentheses, and oftentimes we're minusing a negative value, so we got to make sure we keep that straight. Okay, so I'm going to sum up these fractions. That's going to give me 7/6, and when I sum up these numbers, it gives me -10/3, and 7/6 minus -10/3 is adding. I get 4.5 or 9/2 for that one. Okay. All right, next one. Here we've got some trig functions, sine and cosine. So we should be familiar with what those graphs look like. And so I graphed the sine in blue, and remember that one starts at 0, 0, and then the scale is in radians, counting by pi/2, so that's convenient for graphing these trig functions. So here's our sine curve, looks like this, has a period of 2 pi, so we do one complete cycle in that 0 to 2 pi interval. Cosine, similar, we have the period of 2 pi, but this one starts at, 0, cosine of 0 is 1, so it starts up high, and then cosine of pi/2 is 0, and so on. We go cosine of pi is -1, and so we get this shape, and we finish up at our, cosine of 2 pi is again 1 again. All right, so as we look at where we're bounded in this region, it looks like we're bounded where they intersect here and here, and in that interval, the sine graph is the bigger, or the top function, and the cosine graph is the bottom function. Okay, important points of intersection would be here and here. And if you recall some of the basic trig values, sine and cosine are both equal when we take the cosine and sine of 45 degrees, which is pi/4. So that would be where we're intersecting here, pi/4. And then also when we move into quadrant 3, at 5 pi/4, we're going to have the negative. They're both √2/2. Cosine of pi/4 and sine of pi/4 is √2/2, and 5 pi/4 would be a reference angle of same thing, pi/4 or 45 degrees, and so that would be negative √2/2 for that value in quadrant 3. Okay, so that kind of tells us our bounds. So when we set this one up, we're enclosed from pi/4 to 5 pi/4, and we're going to subtract sine of x minus cosine of x. Okay, so when we integrate here, remember that the antiderivative, or the integral of sine of x, is negative cosine of x, and the integral of cosine of x is just sine of x, so the subtraction stays there. And we're going to evaluate that from pi/4 to 5 pi/4. And so in putting those values in, we see that we have cosine 5 pi/4 minus sine 5 pi/4. And so, cosine and sine of 5 pi/4 are both negative √2/2, right? But these already had negatives, so they kind of cancel both those negatives off. we end up adding those together and just getting root 2 for that. Okay, then as we subtract, remember to use parentheses here, and we're subtracting. Now we're going to go, right here, we've got, after we've done our antiderivative here, so it's negative cosine pi over 4 minus sine pi over 4. So cosine pi over 4, root 2 over 2, minus sine pi over 4, minus root 2 over 2 again. So we get negative 2 root 2 over 2, which is just negative root 2, but minusing the negative, so that kind of cancels and makes a positive. And so we have root 2 plus root 2. The total answer is 2 square roots of 2. Okay. Next example. So here it says curves that intersect at more than 2 points. Okay. So when we have curves that intersect at more than 2 points, in other words, there's going to be like kind of 2 regions here where the top function and bottom function kind of switch places, right? So when we start this one, we've got a cubic function and a quadratic function. Now, you probably would, I might graph these with a graphing utility and get a sketch. You can make a table of values, and it's easy enough to, I set it equal to 0 to find my x-intercepts, which are usually pretty important for graphing. And this was a parabola, so I mean, you can graph a parabola, just find the vertex, and it just has the standard shape, but it's opening downward. It's a little tricky on this graph because the scale on the y-axis counts by 2's. Scale on the x-axis is 1, so be a little careful with that. But you can sketch out these graphs. Okay, so we get our graphs like that. Okay, and like I said, we have the cubic function is the top function starting out, and the parabola, the quadratic function, is the bottom. And so where they intersect, is important. So they intersect here at an x value of -2, and it's 0. Okay, so from -2 to 0, we're going to take f of x, which is our cubic, minus g of x, and that'll give us one area. And then to get the total area, we're going to add to that, and we'll write a different integral after that. We'll go g of x, which is the parabola, minus f of x, the cubic, because they kind of switch positions and give us the pink area. All right, so this is our setup from -2 to 0, so -2x coordinate to 0, that x coordinate, f of x minus g of x, and then dx for our variable of integration, plus, and then we're going to go from 0 to 2, g of x minus f of x dx. And now I kind of did the simplifying before so I didn't have to write so many terms out, but if we subtract f of x minus g of x, you can see that the negative x squared term is the same, so that's going to basically cancel, and we can combine minus 10x and then minus 2x we'll be subtracting, so it'll be minus 2x, and so that would go together for a negative 12x there. And then when we subtract them the other direction, well, same thing, it's just they're going to have opposite signs, right? So when we integrate here, you just use your power rule. We should get 3/4 x to the 4th, and this one would become minus 6x squared. We'll evaluate that from -2 to 0. Similar terms here, just with opposite signs from 0 to 2. And inputting our values, f of b minus f of a, we end up with 0 minus, and then this turns out to be -12, so 0 minus -12 is positive 12. Over here, f of b minus f of a, we end up with -12 plus 24, and then minus 0, so that's just 12 again, 12 plus 12. We do get an area of 24 for that one. Okay, so I'm going to stop with this example on the first video, and I will continue with the last examples in the next video.